Yeah, so back propagation won't be there in detail, but we'll cover that. Okay, so yes, we'll have another session for that. Yeah, we'll cover back propagation of TNL. The quiz two syllabus will be week 5 to 8. So
Sir, but in mail it said 1 to 8.
um, so 1 to 8 is there, but the questions will be from 5 to 8. But what we expect from that is little bit of back propagation or so week 1 2 will definitely won't be there, which is like a Taba function, such things won't be there. Uh, little bit of where it starts from neural network designing uh, architecture of simple neural network and then that kind of thing. Uh, Optimizers. So you don't actually need to remember it. The equation will be given for the optimizer, how optimizers, which optimizers to use, and what is the equation of that. But yeah, questions can be there on optimizers. Not released. Yeah. Yeah, so it's not released. Okay, I'll inform to the person that has been released. Uh, I'll inform them. Think it will be done. Uh, I don't know what time it will take, but I'll do it. Now, so related to week 6, you can ask any question. You can cover that.
Sir, week 5 is covered in previous session.
I guess yes, it was covered. I'm not sure. Uh, Karthik took it. So if you have doubt for that, you can ask that also. No issue. Week 5 I'll
Okay,
solve
sir.
it.
Yeah.
Yeah. So anything week 5 6, anything any question you have, you can ask.
Sir, can we go for an bias variance and training error test or a comprehensive summary? Lot of derivation is there.
So that
And the L2 regularization is there, and the derivation we have some doubt.
um, class, but this derivation a little hard to remember it. I'll try.
Then, sir,
Not
what
sure if
question I should ask?
I'll try. So I'm presenting my screen. Visible. So, so what doubt you have in this? Can I try? So, okay, so what is the thing with bias variances? So let's say you have two different models. One is very complex and one is relatively simple. So a simpler model will always will not have much more variety, right? So it will always predict in similar manner. It will be very close to each other. All the I mean, so you want to train the simpler model with different training samples. You can think like that, or a training sample coming from one set of training problem, and you are resampling it. Like so you are not taking all of them, but you're taking few of them, something like that. And so if you take few of them, of course the the loss will be different, and the uh, the model will be different, right? So the training will have different parameter values after training is complete or something like that. So that's what you do. So you have a relatively easier or simpler model. Uh, One is that, and another is complex model you have. So if you plot like this, so the straight line is a simpler model, which is like W1x plus W0 linear regression kind of thing, right? Then there is another way which is a very complex model. You can build like this, like many curves can go. So this curve is, I guess, it's a sinusoidal curve which was taken. So that is a true value. But generally we don't know what does the function looks like, right? What we know is we know that we are going to predict the loss using, let's say, cross entropy or mean squared error or something like that. But how does actually loss looks like with respect to parameters, we don't know. That's why we require this Taylor series approximation to find the nearest point from a point, right? So we know the value of the loss function where the the W's are there, right? So yeah, so let's say loss with respect to all the parameters, right? So this value I know, but if I change theta to something theta 1, then I might not know what that could be. But this can be, if it is very close to theta, all the parameters, then actually I can predict using Taylor series. So that is the case, right? Okay. So now comes the picture of what is this bias and variance and how it can help in uh, or what we need with bias and variance, right? So let's understand bias. Yeah, yes, Ravina.
Sir, I want to ask about the goals. Sir. Like, is our goal is that to reduce both bias and variance, or like there is a trade-off between them? If we increase one, the other will reduce. But sir, the main goal is it like we have to reduce both of them to get the ideal model? Sir, I'm confused in it.
So generally that's what we wanted. So higher bias is kind of, you can think like that, it's an inability to fit the the actual model, right? So if it is enabled, then we don't want. And higher variance is something like it is predicting uh, way out of, like it is predicting very differently all the time, right? So that's also we want some kind of generalization. So we want low variance and we want a better fitting also. So that is low bias, right? So that's what we want. Um,
But
yeah. Yes, you can. You go ahead.
no, you just add up to the formula. I have some problem with the formula.
Okay. So bias is what we did is so we took, let's say we had some training samples, right? Let's say anything, like let's say 1 million or something. Anything could be there, but let's say 10,000. You take a 400 sample from that, another 400, another 400, and you train this simpler and complex model, right? So you will get multiple this f of at x. So each of them I'm calling it as f of at x. You can maybe subscript it with 1, 2, 3, kind of that. So each of that you get. Now, if you take a
Sir, I don't
average,
understand. Sir, I don't understand how the multiple f dash x is coming. So, am I calculating the multiple functions?
no, same function. So you start with the same function, but you, let's say, uh, so let's say this is the function you started, right? For some random value, you will start from there, right? So that's what you'll do. But you have 400 points only, and you train it, and the complete training is complete after some. You can take some epochs also, no issues. But this 400 points only you will use. Now you will use different 400 points. It might be same also some of them. That is also okay. But now you are using some different 400 points. So now this will converge to different values of W1 and W0, right? So
Yes.
that's what this f of x are different in that way. So we are not going to use one. Uh, so this f of x, when this 400 points are used and trained, everything is done. We'll call that as f of 1x, right? So f of 1x. Now we'll forget about this. I have this model, but I don't do anything further on that. Now I'll start again here. Same scenario. I'll start with different points. Then different points. So the samples are changing, and maybe let's say initialization could be anything. You like whatever like initialization, something like that. So, but let's just understand that. Let's just think that initialize is same. All of them are initialized same way. You are using different samples. That's all. So you will have multiple f of x, right? Okay.
So, sir, can I say from that formula that it is saying that mean of the error, how my value is, how much differ from the mean of the mean, how much my actual value is different from the mean? That is, it is saying bias, that formula. What is actually
Yes,
saying?
yes. That's what we are trying to. So we will now take average of all the functions, right? So we get multiple these functions. We take average of that, which is expectation, and from average we are seeing how the true f of x. So this is a true f of x
But sir,
model, which how far it is.
sir, in expectation, sir, we don't divide like what we studied in statistics that we have to multiply the probability with the random variable. So there is no division term, but whereas we in average we take a division by n or by batches and something like that.
Yes, that will you do. Like uh, let's say you got one and I can't actually. So let's say you have this plot and this plot and this plot, something like that. You have to average it. So all the values you are going to do this averaging. But let's say for one some some point I'm taking 1 point of all this three, if I can. So let's say 1 plus 2 plus 3, that would be there. So we have 1 2 3 kind of. Then I will divide by 3. That I have to do. So this is average or expectation, anything you can take. So expectation was always average, right? That's what we used to do in statistics also. Um, okay, fine. Okay. So I hope that is okay. So we have this expectation average of f of hat x. Okay. Then I subtract with the true. So that's what we want. How far it is from the true function actually. So true function is this red curve, and maybe this green and blue curves are the one which we have uh, written. You are taking expectation of that. So this blue and green are expected curves, right? So you got from multiple samples you have taken and trained it. So that's how you got it. It's a average value of kind of here mentioned, but uh, now true is the red one. So that's what is there. Now okay, we'll finish to explain here. Now what is variance is? Variance was always like let's say you are doing x minus x bar square or mu x square, something like that, right? And for each point you would do and sum that up, something like that. Or yeah, so similarly you are doing here that f of hat x you are, and you have predicted average earlier, right? So this average was predicted expectation. Now you are subtracting that and squaring that and finding expectation of that, right? So that's what variance is also. If you, because when random variable starts, this variance definition would have come. Uh, this term is just that. Now that's what a variance is. Now what we wanted to do is um, so this is kind of taken, you can think like a simple model is there which is high bias. So it is like, you can think of inability to fit, right? Inability to fit. So that's what a bias is. If it is uh, like not fitting at all, that is high bias. But more complex model has very low, like it has low bias, so it is actually able to fit the curve. But there is a problem with the variance here. So it's not, so this blue curve is not worrying much. Prediction wise, it is always giving you kind of similar output, but here the prediction could be anything. Like it is in a very disarray manner, right? So this high variance kind of thing. So we have to trade off between that. So what should we do? Should we go for more complex, or uh, should we have to come in between of this, right? That is the idea. So how can we do that? Uh, so we'll see what we can do before we come to the regularization, like why regularization actually works. So um, okay, so uh, this just believe that okay, this equation is true somehow. Okay, so we'll not go into actually proving that this equation will come, but you can try. But so let's say we have bias square, variance is there, and some reducible irreducible error. Okay, so we can't do much with that. There is nothing we can control here. But if bias is high, then so this is a loss, right? You can, it's a like squared error. Okay? So squared error is there. So we are predicting y. So true y is there, and f of x you got y hat. You can think of it as y hat, and that's what we do, right? Y hat minus y square, and then take if you take average of that, then it will become mean squared error expectation. So you have bias and variance. It is in a form of that. So if you have high bias, then also there is an issue. If there is a high variance, then there is also issue. Okay, so you want both of them low. So you want low bias and low variance as well. So that is the idea why we need both of them low. You can take from here that this there is summation of both of them. Okay? Um, now trade off,
Sir,
that is.
but sir, in this equation, will it the bias high will be more dangerous than high variance?
Um, that is uh, what is more problematic. We can't say uh, from this equation, uh,
Because sir,
but
it's square term, so if it is high, then it will raise to a loss at a very high value. I thought like this.
but but no. See, actually, variance is a square in itself, right? It's a sigma.
Yes.
Let's say some square, right? So
Yes.
it's not like that. That this bias will. I mean, this could be in smaller values and this could be in a higher values. So uh, I can't say actually which is better, or you can't compare that. I don't think so that is possible. Um, so now what we are interested in is so what we are so what has been explained in the courses that we will go and see train error and then test or test error in any order, but we'll see that and how which error is more important uh, than the other, right? So which error actually you should look for is being explained. So you know from the let's say ML also that when you are doing machine learning that we used to find validation errors, train validation split we used to do, then find validation error. If it is very far or we actually uh, uh, think more or we give more weightage to the validation error, right? Than the train error. Even if train error is very low and validation error is high, then we certainly uh, we said that it's overfitting case and all, right? So we apply the equidation after that. So maybe that point was not explained why, but or MLT it was, I'm not sure about that, but uh, so that's what we'll do next. That why test error is more important, or you can consider validation error also to this. Okay. So what we are assuming is that let's say there is a true function that exists. Okay, we kind of don't know that, but that it does exist, and that is like this. So f of x, and some error also we are considering that if you do that, then that is a true value of y. Okay. So um, okay, so now um, so we have some, but yeah, let's just skip this. But uh, this is what we wanted. Right? We wanted uh, to find the uh, mean squared error to be reduced, right? So we'll expand it a little bit. So now I'm saying that y is a f of x plus epsilon, right? Now what I'm doing is I'm taking this as a and this as a b, and you know f of let's say uh, a minus b whole square, right? So you can take this as a. That's what we are doing. A square then minus 2ab and then b square, right? So that's what being done here. Then uh, and you know that expectation of sum is sum of expectation, something like that, right? So each you can take individual expectation and if you sum them, then you will get a total expectation, right? So that's what we are doing. We are taking expectation of each of uh, this terms. Now, if you do that, you will come across this. So this is the value you will get from there. Uh, now, you estimate an expectation and then return over deviation. Well, I'm not sure why we have done that, but uh, so, so this is what we have come across, right? At the uh, one slide ago, and so we wanted to find this, right? So that is the idea that uh, we wanted to predict this, which looks like which is coming from there, right? So we have switched the sides. That this is the idea that there is a uh, so this is a true function and this is the prediction, right? So we wanted to do that, like we wanted to find out that. Now uh, uh so why I can't directly, like, let's say why can't I just skip this and use y hat minus y, like That's what we were saying, right? That this is a y hat and y. Because we actually don't know what is this true f of x looks like, right? We have no idea about f of x. We are just so let's say what we actually have. You can think like that. Let's say this is a point, or this is a function. But let's say we have 1 million data points, right? So 1 million data points could be let's say like this, right? That they could be scattered. They could be very near to each other, but we don't have actual curve. Um, and like that, right? So, but what we assume that if we follow across this 1 million points, then we will definitely be, or we'll kind of assume that we'll get the true curve. That was the idea behind it. So that's why we are trying to find what is uh, the prediction one, or whatever we have predicted is how far from the true function, right? So that's what we wanted to find, and that's where it is coming, that whatever y's we know, right? So some y we know out of this 1 million y point we know from the whole function, and that's where we are trying to find the error. But there is some more uh, errors. Some more values are also coming uh, from that, right? So some kind of, you can take a noises there a little bit here and there, right? So that's what we are considering using this equation. Okay. Uh, Now, okay, so we come across this now. So expectation of y hat minus y, you can kind of think like that, and we have said that we are taking this error as a Gaussian from a Gaussian function, right? That mean is 0 and variance is sigma square, something like that. We have taken consideration when we started, or normal distribution. Right? Normal distribution is what we consider. So using that, I now um, how come it has so now uh, I'm not sure if this sigma square is actually this variance, but I don't think so. That is that. So I think this is a different constant they have taken. But this is a covariance, right? So why is that covariance? You can take, let's say, we take that's what we do in COVID, right? We take x minus mu of x and y minus mu of y, and then sum all of them, right? That all the points we sum, and then then there is no, that is a correlation. But in covariance, that is this is there. Now mu of x is 0, um, or in this uh, or expectation of x is 0, because this is a normal function, right? That's why this expectation x is 0. And similarly, I think we are doing something like that here, and finally you'll get this. Okay, so I'm like proving a derivative is a derivation is a difficult, but you get, so that's how we got this function where some empirical error is there, which we will be able to calculate. Uh, kind of this might we might not be able to calculate, and this covariance part, we'll see what we can do with it, right? So this covariance uh, is also coming into it. So when we say that when in reality what we do is we actually calculate this uh, when we take mean squared error, right? So this is a mean squared error we do, but what we need is we need this type of mean squared error where we are comparing a true function which hypothetically like exists, and whatever the prediction or whatever function we were able to make, right, using the neural network. We wanted to compare that. That is the real comparison we wanted, but we can't do that because we don't have that function or not. But we have some points where we can do this, where we can find the empirical estimation of error, and we can definitely find covariance, and there will be some constant error will be there, right? So yeah, so generally that's what we used to do, and this part we used to left out, but we'll see what we can do with that. We- Now comes what you should use, right? What you should use train error or test error. What you should do. So the idea is that uh, that if you use, let's say, test errors, um, then then it is being assumed that, let's say, y was f of x plus epsilon, right? Something like that, or something like that. Uh, but here in test, when we use test point, this epsilon, or it has never contributed to anything, right? So we can kind of say that the uh, uh, uh,
Sir, what is that meaning that perpendicular symbol epsilon is perpendicular and before that also they have said y minus f of x is perpendicular to f cap of x minus f of x. What is that
that is
symbol?
not perpendicular, but
It's not actually perpendicular, right? Like
no,
what is that in
it is not.
graphics?
Uh, I am not sure. I think that would be a mistake also possible, but I don't see any other explanation to this. Like, I haven't seen this as a, I haven't seen anything other than perpendicular usage of this symbol. So I never,
So how it became perpendicular, sir?
no, it is not perpendicular. This symbol is incorrect. It's not perpendicular. And it might, the symbol might be correct, but it doesn't mean perpendicular. So, um, so what actually we wanted is we wanted to the f y minus f of x should be, you know, let's say similar to, or it should be equal to this. Maybe that's what the symbol could be. That that's what we wanted, and y minus f of x is a epsilon because y is f of x plus. Right? So that's what is that. So uh, now we wanted to find the expectation of this guy. So we multiply this expectation with this expectation, but uh, okay. So that's the idea is that the error we are trying to find now should be right. So this validation set is independent of training set, right? Let's say you might have seen this, that let's say x and y is there, but if they are very they affect each other, then there would be high covariance or correlation, something like that, right? But if they are totally unrelated, then there would be very low covariance or could be zero, right? So they are not related. We can say that. And that's what we are trying to prove, that the validation set has no participation in predicting the estimated function, right? So this is the estimated function or f of hat x we come across, which has so this function was produced by using training set only, or it is not being there is no contribution of test set in this, right? So if it is true, then this covariance will become zero, right? So this will become zero, and you can see that now this estimation error or this mean squared error could be a correct estimation of the loss we are trying to predict, right? So the loss we wanted to look for when we do uh, model training is test error, not the training error or validation error. Why we should not look for training error is because in training error um, it was kind of related to the training set. So now I can't say that this epsilon and f of x are not related. They are related, and there would be some error which we don't know, but it won't be zero, right? That's what is there. So, so empirical train error is smaller uh, uh, than the true error and does not give a true picture of the error. Okay, so it will not actually give you a true picture of that. Okay. No. Why it should be smaller that picture, but so it doesn't give you the correct picture, right? That was the uh, idea we have to take from that. Now that some science lemma will come, which first professor has explained what is it, but it is something like this. So you take a derivative of the predicate function with respect to y, and and you compare it with it. So if you do that, then so something he will do, and the explanation is that you get a true error, which is empirical train error, and then some small constant, and there is some uh, model complexity, right? So here, model complexity will come into picture. That why we should not make a much more complex model. So if you make a complex model, then and we can't actually predict this, because what we actually can calculate is this part. We can only calculate this part. The small constant will be there, but we generally ignore this. So while doing the actual when we do the training and all, we always ignore that. Okay, we have never touched upon what is the small constant. Now this part is also there. So in true error, this three components were there. We were only considering one component, which is this empirical trainer, and we have ignored other two, but it is there, right? So this model complexity was always there, but we have never considered it. So to consider this, that what should we do with this model? If it is a complex model, then of course my true error is actually high, and my empirical error can't capture it. Okay? So that's what will be there. But um, that we will come. So some more complex terms will be there, but what will come across is we have to do the regularization, right? So because regularization is the only thing which will look into the complexity of the parameter, right? So whatever, let's say, loss was L theta, then we will use some, I mean, earlier it used to be lambda, but now we'll use alpha, then all this theta, right? Or you can take W's, alpha W will use. So this regularization parameter will be there, and will use some form of this, right? So if it is square, then it is L2. If it is just this, then it will become L1 regularization kind of thing, right? But in this course, we'll mostly cover L2 regularization. I think L1 is not covered. Okay. Uh, Now, I mean, L2 regularization you're familiar with what we just saw now. That earlier we used to take this loss, but now we'll take square of that, and we will take alpha by 2 just for easier purpose. So when you take a derivative of loss with respect to W, it will cancel out, right? So you will get alpha 2W, and if it is alpha by 2, then it will cancel. So that's why alpha by 2 was taken, but you can take this as a regression parameter. Now, okay, that's what we'll do. Here, same thing. Now, a lot of math, but so this I would suggest you to go with the course uh, video, where he has tried to explain everything in detail. I mean, as much as he can, but uh, now what we are trying to do is what I can say, but the crux I can say is that let's say we have some parameter, right? Let's say W1 to Wn. So if you do all of this complex math, then you'll come across this part where it will be, that uh, so actually what we did is we have this LW and let's say tilde. So LW plus some alpha by 2 times W square, right? So what we are doing is so if let's say this value W is a parameter value, right? So if this parameter value is high, then we are penalizing the loss, right? So that will increase the loss. So we kind of wanted to penalize if this value is too high. Right? So we wanted it to be in the moderation. It has to be in some moderation, right? So why it works is if you do this eigenvalue decomposition and all, you will come across this where it will should be like this, right? So lambda 1 by lambda 1 plus a, right? So wherever eigenvalue, so let's say this any data set is there, a high eigenvalue kind of represent that um, that no, kind of, you can say, more important, or it's a principal components kind of thing, right? That higher eigenvalue will represent that has uh, more data points lying in that dimension or that direction, right? So if that is the case, then we wanted to consider that, like, if that features we will consider, but we will ignore other features, kind of that, right? So that's what we'll do using this. If there is a higher eigenvalue, then we'll consider it. If there is a lower eigenvalues, then we'll kind of ignore that using this regularization term, right? So it's a proof of why it will work. You can try it. I won't go much into it. And similarly, the same thing is trying to explain that. Uh, so other terms of regulation is you can do augmentation, which is very similar, very easier. You just so in terms of images, you take image and you rotate by some angle, and you get other images, and you get more training data, right? So more training data is like better for learning, and it's a very variety of data also. It's not the similar data. Like if you give this 1,000 times, it will not affect. But if you rotate it or do some kind of other blurring or any kind of thing, then it will affect the way the model learns, right? So that's what you can do. So there will be another this image one. Uh, there will be some similar kind of augmentation we'll do later. So we'll come to that. So parameter sharing and tying is I guess it's not covered before, but what you do is let's say you have some weights here. You'll use similar weights here, or maybe weight transpose of that, right? So if this is, let's say, uh, 10 neurons in this, or 10, you can think, 5 here. So this should be like 10 cross 5, right? Like kind of, then this should be 5 cross 10. So you'll use same weights here, weight, and that there will be weight transpose, right? Uh, uh, so whatever updation happens here, it will update here and there also. So it will change directly. Like you'll not use different weights. Like at one go, you are kind of updating it 2 times. Right? So same thing like that. So that's called parameter sharing. You'll do. So in CNN, what we are going to do, check in week 8, that will make a filter. So this is called a filter run and all, which will use um, throughout the image and capture the important feature using that, right? So this will come in week 8. We'll cover that how one filter can help in capturing image data. Right? So something like that, we'll see that. Now you can add noise to the input or output. So I guess input. So if you add noise to the input, that is kind of an augmentation, right? So you had a date, you had some input, let's say x1, x2, x3, kind of. So this um, let's say this one data point at x1 of 1, and similarly you can have 2. See. So, okay, so these 2 data points are there, but what you can do is you can maybe corrupt any few of this value, right? So this is a vector which will go inside, but you can corrupt it, right? So you might add some noise to it, any normal from a normal function or anything. You can add some noise to it, and you can send it to the thing. So this is another form of, like, you can say, augmentation we are doing, and what we'll do is it is kind of same as L2 penalty. Like you can think of it as yeah. So this derivation is that you are going to do this y tilde minus y square. Now we don't have y hat, but we have y tilde, and uh, so that is so y tilde is coming out to be from here, right? Y hat minus something like this. So sorry, y hat plus this, which will substitute here, and you'll get this. Now you are taking that. Now some form of reformation they would have done, because they are calling this as A and this as B, right? So y hat minus y, they are calling that as A and B. Then this A square plus 2ab plus b square, right? So that's what is there. Now, uh, now this was similar to the this term, yeah. So this term is kind of similar to the covariance thing we did last time. With here, if it is they are independent, it will become 0, right? So that's what the idea is. That makes it 0. And if it is 0, then we'll have this, right? So this is very similar to the L2 now, which was LW plus some alpha by 2 and W square, right? So that's what this looks like. So now you can say sigma square is kind of some constant would be there, but uh, it is L2 kind of penalty it's becoming, right, by default. So if you do this, you can add some noise to it, to the input. You can change few numbers in this and in a vector and something like that. That would lead to L2 regulation. So you can think that we earlier, when we did this augmentation, this is also L2 regulation. We're kind of trying to achieve that. Because there also pixel values are changing. If you rotate or something, it will change. Okay. Now, partly okay, adding noise to the output is very easy. What we do is we take out some value from that, okay, and then we divide or we distribute among all the other terms. So it will be, let's say we have 10 here, so this will be 1, but rest is 9, right? So we'll add epsilon by 9, epsilon by 9, and epsilon by 9. So we have subtracted from this, so it will become 1 minus epsilon, right? Yeah. So we'll say that this is a true target, right? So this is a hard, this is called hard target. But if we do this, and it will look like this, so this is called soft target. Now, if we do the cross entropy loss calculation, then earlier we used to skip all of them, right? So that's what we used to do. That we used to ignore the um, other terms. That okay, whatever it is, we don't care. We care about the true value of that. But now we'll kind of include that also in loss calculation, and So yeah, so it's like instead use so do not trust that true level. They may be noisy. Instead use a soft target. So it's like you are kind of taking a little bit of thoughts or inputs from the rest of the uh, not just a true label, but which are not true also. You are taking their inputs also. So some form of probability they are also getting it. Let's say the true one got 0.6, but somebody got 0.2. Somebody got maybe let's say rest of them got 0.0500 something small value, but the 0.2 is also telling something, right? That it might be it might also become a true value or something like that, right? So if you do this, then it will try to correct it more. That okay, not this is not enough. We might have to do something more. Right? So it's like that that we are taking loss from other targets also. Now early stopping is very easy. That we don't want our model to train itself, then do overfitting, right? So if we let it go for more epochs, then it will overfit, and overfitting will leads to higher variance, right? Higher variance. So that's what we don't want. We will let it run for some time. Then we'll set some rule that okay, let it run more p more times, which it will do. And then after p times, it will, if it is increasing, then we will stop there. Will not let it run further. We'll come back here. So whatever was loss value here will go there, and we'll take out this weight values. Okay, whatever was there in the iteration. Let's say so iteration start from 0. We reached at 100, where we got the best one, and let's say we set a step size that after or in next 5 uh, epochs or next 5 epochs, if it will increase, then I'll stop, right? So we are now at the 150th epoch, so we'll stop there. We'll come back to the W100 and all, right? So let's say we start from W0, then we would have reached W100, but we'll come to W at the end we have 105, but what we'll do is we'll come back to W100. So that's where all the weights are there, which were used in 100 epoch, and that will become our the the model, right? So the model will have this weights value. Okay? So that's what early stopping is. Now, yes, same thing we are trying to do. How far? So T you can choose anything, any 5, 6, 10. It's up to you. Shall and control the space of exploration. Uh, now maybe they are trying to explain how mathematically work. But I'll skip that. Now ensemble, you would have seen ensemble in terms of bagging and boosting. So here we'll not do boosting. We'll only do bagging in ensemble. So bagging is something like you train multiple models and you take, I guess, voting from them or average from them, right? So any form, if it is classification, voting, otherwise it is averaging. So that's what we are doing. That's let's say if that's what we wanted to do. Then what? Um, uh, so yeah. So let's see before that. But what happens actually when we take a bagging, right? So how this bagging will affect that, right? Um, so if you solve this, you'll come across this, right? So this V and C. So V is variance and C is covariance, right? So let's say um, what can I say that yeah. So let's say this model, right? So this multiple models are there. If they are completely correlated, uh, okay, then the V will be equal to C, right? So if they are completely correlated, that will not actually give you different opinion, right? So why we used to do bagging and in terms of like let's say uh, theoretical or thinking wise, why we used to do bagging? We wanted different kind of opinions from the model, and then maybe we would be able to predict better, something like that. So if they are uh, not um,
Sir, what are variances in this?
what are variances?
C is correlation.
Yeah, so no covariance. V is variance.
Covariance.
The earlier term which we use just in understanding of bias and variance, right? Same thing. Yeah. So if they are highly correlated, right? So if they are highly correlated, then the loss will become it will be uh, so if let's say V is equal to C, then you will see that it will not do a better job. But if they are uncorrelated, which we wanted them, then C will become 0, and if this is 0, then you can see the loss is uh, reducing, right? So uh, to reduce the loss, we want uh, uncorrelated uh, models. Models should not be correlated; they should be uncorrelated. That is what we wanted. And if they are correlated, or if all of them are correlated, then it will this term uh, will increase. Okay, so this will increase, and it will lead to higher increase in loss also. Uh, right. So maybe if we do this, if we do bagging, we might end up in between this scenario somewhere. Some of them may be correlated and all. So that's what we wanted. Right? So we don't want correlated models. We want uncorrelated models. That's what we can take from that. That why we should do bagging is that will give you multiple opinions, and you can then take a uh, call based on voting or something like that. That's what bagging was always. Now we can't do this type of model training where multiple models are trained, then we take opinion. So there is something called dropout was introduced, which will do similar thing. So we'll see what is being done. That let's say you wanted to train uh, uh, train multiple instances of the same network using different training samples. So these are some options given that you train several neural networks with different architecture, and or you can train multiple instances of same network using different training samples. So you can sample different samples and then train it. That is also bagging, right? So uh, to do kind of bootstrapping or something like that. Right? So choosing features and all depends on you which way you do. So this two ways are there, but both of them are very expensive. Even one training was always expensive in deep learning. So what can we do? So what we are going to do, we are going to remove some of the neurons. Let's say this neuron or some neuron was removed. Uh, so we kind of do with a uh, so generally what we do is we try to not remove in most of the cases, right? So what we do is we retain it for a probability of 0.8. Generally, that's what being used. That for 0.8 times, like that many times, I am going to retain. So retain is keeping it. Like I'm not going for that, but this right. So that's what we'll do. So now, if you do that, it will look like a different model in each case, each time, right? So let's say once it was removed, but in next case, maybe we can have different architecture, right? So from this to that. So these are two different models, and they works uh, perfectly fine. But what actually happening in this is that whichever has model has contributed or whichever element has contributed um, in most of the time, that meant time it will get updated, right? Let's say once we we do the forward pass using this weights. Now, how will it will back propagate using those weights only, right? So it's like you can take uh, so let's say you got loss, right? So loss is uh, something y hat minus y whole square or something. Right? So mean square, cross entropy, anything you can choose. So that you'll do. Now y hat is going to be, let's say uh, w x, or if you use softmax or sigmoid, that also you can do. So wx plus me here look like a regression problem or something like that. But anything like you can choose a sigmoid also. That is also okay. So something like that y hat would be. Now here I'm using w1 only, but it could be multiple w's could be used and all right. So whichever w, let's say this some w didn't contribute it, right? So while doing back propagation, we'll not update this one, but we'll update this w. So this weight will get updated, but this weight, because it didn't contribute, will not update it. And similarly, that's what we'll do here, here, and that, right? So wherever it has contributed, we'll go back and update that. So it's possible that some weights got updated 1,000 times, some got updated 50 times, some got 100 times. Anything is possible, right? So it's a random process. We randomly set it with a probability of 0.8 that we are going to retain it and all, right? So now, uh, now how will we going to um, do the prediction, right? So while training, we did that, but while testing, we will not remove them, right? So testing will keep all the uh, weights, right? So maybe let's say this weight was updated 100 times, this weight was updated 200 times, this weight might have been updated, let's say 400 times and all, right? So it could be updated different times, but at last some value it has, right? Now some value is there. So whatever that value is, we'll use that and we'll do the prediction simply, right? So at training time, present with a probability of 3, right? Now at test time, uh, what we know is, we know that it was present with a probability of 0.8, right? So we know that it was present at 0.8. So that's what we'll do while testing. That uh, yeah, so uh, so instead of using full network, uh, we will scale the output of each node by the fraction of time it was on during the training. Okay, so I mean, I know that we actually have the count that how many time each was on, but that's what we are not going to do. Like we are not going to keep a let's say a timer or any counter. We are not going to keep that will say that no, this was present this many time, 50 time, 100 time, something like that. But what we'll do, we'll rely on probability. We'll assume that we have trained it enough time. It has all of them have gone through enough cycles that now each of them, the probability of each of them weights is going to be some value, right? So we'll rely completely on probability. We'll say that whatever output uh, it will produce, we'll multiply that with the p. Okay, so we'll not use w1, w3, but we'll use pw1. So whatever values you got, you have to multiply that. Let's say it got 0.5, then you will multiply it with 0.8. It's something like that. Then you'll use this uh, to produce the output. Okay? Um, there. Now, I guess we can maybe group them in different ways. That's what summarizes. Um, but so you can actually group them in different ways, maybe based on data architecture, optimizer, penalize, cost, or you can maybe group them in explicit or implicit way, right? So there's two ways you can group them. Yeah, guess that's all there in the week 6. You can read further this thing if you like. Any questions? Okay, then I guess there are no doubt we can close the session. Okay, then goodbye everyone.